Hello. In this video, we are going to derive an expression for the hydrogen ion concentration in an aqueous solution of a very dilute strong acid. Let's suppose that we have some strong acid in aqueous solution, which we will represent generically as HA for just some typical strong acid. We know that in aqueous solution, it's going to dissociate completely, because that's what it means to be a strong acid, into a hydrogen ion, H+, and the conjugate base, which is going to be the anion here, A-. Recall also that if the acid is dilute, then the only major source of hydrogen ion is from H+. Now we also know that there is a second source, or we should know that there's a second source of hydrogen ion, which is the aqueous solution itself, but so long as the concentration of HA is greater than 10 to the minus 7, then the only important source of H+ will be the strong acid. So in that case, we can make the assumption that the concentration of H+ is essentially equal to the original concentration of the strong acid. We recall that the pH, by definition, is the negative log of the concentration of H+, which in this case is going to be exactly equal to the negative log of the concentration of our acid at the beginning, at least. And this is the standard technique that is used in general chemistry for the general case of a dilute strong acid. This technique will not work when you have a concentrated strong acid, as you will learn in a physical chemistry or analytical chemistry course, where we have to invoke the concept of activities. The usual threshold where a concentration goes from being dilute to being concentrated is generally about 0.1 molar, 10 to the minus 1 molar. Any strong acid that is more concentrated than that, then we have to use the concept of activities, and this formula will lead to incorrect results. So, if dilute means 10 to the minus 1 molar, what do I mean by very dilute? So very dilute means that the concentration of the strong acid is in the same range as the normal hydrogen ion concentration for a pure solution of water, which would be 10 to the minus 7 molar. So if the concentration of the strong acid is in that range, we cannot make the assumption that the only important source of hydrogen ion is the strong acid, and we have to take into account the fact that some of the hydrogen ion that is being generated is formed from the solvent itself. Now, if the strong acid has a very low concentration, if it is very dilute, then we have another important equilibrium going on. And that involves the solvent, water itself, which we'll just write as HOH here to highlight the dissociation. And we recall that water will auto-ionize. It will break up all by itself into a hydrogen ion and a hydroxide ion. Notice that for the sake of brevity and for less writing, I am writing H+, where you might have been taught to write the hydronium ion H3O+. If you prefer to write it that way, feel free to just substitute in any case where you see H+, feel free to write H3O+ in instead. Now, an important difference between the first reaction and the second reaction is we write the first reaction with a single arrow because we have a strong acid, and strong acids by definition break up completely. This reaction goes to completion, so that for every one molecule of the strong acid we start with, we're going to get one H+ ion and one A- ion. And because the conjugate base is weak here, this particular ion will have no further effect on the pH properties of the reaction, so we can ignore what happens with A-. But in the second reaction, we have to write two arrows because for each molecule of water that we start with, not every single one will break up. In fact, only a very few of the water molecules will dissociate. So we have the equilibrium constant for this reaction is a small number, and it's an important number to commit to memory. And this number at 25 degrees centigrade is 10 to the minus 14. So only very few of the water molecules will dissociate, but because some of them do, a great many of the properties of aqueous solutions follow from this fact. So now, before we move further, let's notice some stoichiometric relationships that we have already. The first relationship is to know that the initial concentration of the acid is identical to the amount of hydrogen ion that we get from the acid. And we know this because of the fact that our acid is a strong acid. So we see that the strong acid is one of the sources of H+, and we're noting that it's the source of it by writing a subscript of HA. This is often written, you may notice this concentration of HA, you may see in a lot of books written as C sub HA. For the rest of the derivation, I'm going to continue to use the square brackets to be consistent, but notice that if you look in many textbooks, this quantity is written often as C with a subscript of HA. Let us also write an equation to remind ourselves that we have two different sources of H+. So the total amount of H+, we're going to write as H+ with a subscript of tot for total. So we know that some of the H+ is going to come from the strong acid, which we saw right up there. So that is our H+ here. But notice also that we're going to get some H+ from the auto-ionization of our aqueous solution of water. So we'll put that as sub H2O. So also notice, so now we're going to make a algebraic assignment, and we're going to use the variable z, and we're going to set this equal to the concentration of H+ that comes from the auto-dissociation of water. So that's going to be our variable z. It's going to be equal to one of the sources of H+. And the reason why we're doing it this way is we're going to make use of the fact that when water auto-ionizes, for every single H+ we get from water, we're also going to get one hydroxide ion. So we can also, at the same time, set Z equal to the concentration of hydroxide ion. And we're going to omit any subscript because in this particular situation, we only have one source of hydroxide. Hydroxide is only going to come from the autoionization of the water solvent. Now we are going to make two simultaneous substitutions into this equation for the total concentration of hydrogen ion. So just to explain first what we're going to do, for the H plus from the acid, we also know this is exactly equal to the initial concentration of the strong acid, which we could write as C sub HA in many books, but we're going to write as HA sub 0. So we're going to substitute this expression for the first term here. Now, the second term in the H plus total expression, this term here, we notice we've assigned the variable Z. So now let's rewrite this particular equation, making both of the substitutions at the same time, just to save some writing here. So we have an expression for the total concentration of hydrogen ion from all its sources. One of the sources we saw is from the initial dissolution of the strong acid. And the second is from the hydrogen ion formed from the dissociation of water, to which we've assigned the variable Z. So now we have that the total H plus concentration is equal to the initial concentration of the strong acid plus our variable Z. Now we want to write down the equilibrium constant expression for this second reaction. So recall that in the numerator of the equilibrium constant expression, we always are going to write the products as a product. So we have the concentration of H plus times the concentration of hydroxide ion. And then typically in the denominator, we would have the concentration of the reactant. But since water is a pure substance, by convention, we omit the concentration of undissociated water in the equilibrium constant expression. So that just leaves the concentration of H plus times the concentration of hydroxide is equal to Kw, the auto-dissociation constant for water, which is equal to 10 to the minus 14. And now just, we will omit it later on, but just one thing to keep in mind is that when we write the H plus here, this is H plus total, because this covers all the H plus in the solution. And the OH minus is also the total, even though we only have one source of hydroxide. An amazing thing about this particular equilibrium is not only is it true in the case when we have pure water, but it's also true when we have water as the solvent and we have many other species present. Now let's substitute this derived expression into the equilibrium constant expression for the concentration of H plus total. So the leftmost term now becomes the concentration of the strong acid initially, HA, plus Z. So we could write down now the other term, which is the concentration of hydroxide. But we had seen on a previous board, if you miss it, you can always rewind the video to see, but notice that not only was Z equal to the concentration of H plus that came from the dissociation of water, it was also to the concentration of hydroxide that had come from the dissociation of water. So OH minus is also equal to our variable Z. And this is equal to the dissociation constant for water. We can now simplify this expression by using the distributive law. So we have the concentration of HA initially times our variable z plus the variable z squared, and this is equal to the dissociation constant for water. So now let's subtract kW from each side and flip the terms on the left-hand side, which we're able to do because addition is a commutative property. So we have z squared plus the concentration of HA minus kW is equal to 0. And we notice immediately that we have a quadratic equation in the variable z. Now we note that for our quadratic equation, that the coefficient a, the coefficient of the z term, is simply equal to 1. The coefficient b, which is the coefficient of the linear z term, is the concentration of the strong acid initially, HA sub 0. B squared is simply this squared, so we have HA sub 0 squared we notice that C, which is our linear term, constant term I should say, constant term, is equal to minus K sub W. So therefore 4AC is equal to minus 4 times K sub W. So we all have all the necessary parameters to solve this particular quadratic equation using the quadratic formula. So we recall that the solutions to such a quadratic equation in general are going to be negative b plus or minus the square root of b squared minus 4ac all divided by 2a. So now we simply apply the quadratic formula to get that solution Z are going to be negative b, which is going to be minus the concentration of the strong acid initially, minus HA sub 0. Plus or minus the square root of the expression. So now we have the concentration of HA sub 0 squared minus 4AC. 4AC is actually a negative value, so this is going to be plus 4 times the dissociation constant Kw, all divided by 2. Now we recall that we had an expression for the total concentration of H plus from all its sources. And that was equal to the concentration of HA initially. So that's our concentration of our strong acid at the very beginning, plus Z. So now we simply substitute our expression for Z into our expression for the total concentration of H plus, which admittedly will look a little confusing at first. one thing to note, even though this looks messy, is that as far as our plus or minus goes here, since the concentration of H plus can never be negative, this term here will never be negative, which means that we're only going to be examining the case where we have the positive square root here and not the negative square root. So just to simplify for further developments, let me just simply remove the minus sign here, because that would lead to an unphysical and unrealistic solution. The expression that we have derived here is completely general, and the only implicit assumption we've made is that it's reasonable to use concentrations and not activities, which means we are in a situation where the strong acid is not concentrated. But other than that, we have made no particular assumptions. So since this is completely general, it must also give us the correct answer in special situations for which we already know what the answer is. That's an excellent way to double check a derivation, is to look at special cases and see that the results agree. So in the first special case, we're going to look at the situation where the concentration of the strong acid squared is going to be much greater than 4 times K sub W. Okay. So we can solve this further by taking the square root of each side. So this is equivalent to the situation where the concentration of the strong acid, HA, is much greater than 2 times the square root of the dissociation constant of water, which numerically would give us 2.0 times 10 to the minus 7. So now if we assume that the concentration of HA squared is very much greater than 4kW, this leads to the consequence that the expression the concentration of the strong acid squared plus 4kW is basically just equal to the concentration of HA squared. Which is our expression underneath the square root sign. So now, this expression here is now just the square root of the square of HA squared. So that turns this term here into simply HA. So HA sub 0. So now we have minus HA sub 0 plus HA sub 0 all over 2. So this whole term now becomes 0 with this assumption. So that leaves us with, as a result, that the concentration of H plus total is simply equal to the concentration of HA initial. And this is the assumption that we generally make when we're trying to figure out the pH, and before that, the hydrogen ion concentration of a strong acid, simply by looking at the concentration of the strong acid, setting that equal to the hydrogen ion concentration, and then taking the negative log to find the pH. So we see effectively what we've done is that we're making the assumption implicitly that the concentration of the strong acid squared is much larger than 4 times the dissociation constant for water, and so long as this assumption is actually valid, so we actually have a concentration considerably above 2.0 times 10 to the minus 7, that technique, which is taught in AP chemistry, is taught in general chemistry, and is taught in the initial parts of analytical chemistry, will lead to valid results. So now let's make the opposite assumption. So now we're going to assume that the concentration of HA squared is much smaller than 4 times kW. And notice, important to put this down here now, is that this is an equivalent assumption to the notion that the concentration of HA is much less than 2 times the square root of K sub W. So these are equivalent assumptions, and we will use both versions in what is to follow. So again, we're going to look at the rightmost term, the term underneath the square root sign, and notice that with the assumption that we made, that the expression, the concentration of HA squared plus 4 times kW is essentially equal to the square root of 4 times kW, which is 2 times the square root of kW. So now the term underneath the square root is equal to 2 times the square root of kW. So let's write out what this thing is going to be. By the assumption, we have that the total concentration of H plus is equal to the concentration of HA initially plus this expression here we have minus the concentration of HA initially. The expression under the square root we've simplified to plus 2 times the square root of K sub W, all divided by 2. So now we can combine the concentrations of HA, so here we have HA, and then we have minus HA divided by 2, which gives us the concentration of HA initially divided by 2, plus, we can cancel the 2's and we get plus the square root of K sub W, which again looks a little ugly until we recall that since we multiplied this expression through by 2, it's going to show that here we had the assumption that the concentration of HA is much less than the concentration of 2 times K sub W. So again, we could take this expression to be divided by 2 is equivalent to saying that the concentration of HA divided by 2 is much less than the square root of kW. Well, if we apply that here, that gives us that the sum, we can ignore this sum relative to this sum, is going to be equal to the square root of K sub W. And we know that the square root of K sub W is going to be the square root of 10 to the minus 14. So that tells us that the effective total H plus concentration in this particular case, where the concentration of HA squared is much smaller than 4 times K sub W, is essentially equal to 10 to the minus 7. Effectively, if the concentration of the strong acid is sufficiently small, it's as if it is not there at all. We could essentially assume that the only source of H plus is going to be the water solvent itself, and we end up with a hydrogen ion concentration of 10 to the minus 7, which is such an easy problem we can calculate the pH immediately in our heads, and we get that we have a pH of 7 in that case, which we know to be true. If we have an infinitely dilute strong acid in aqueous solution, the pH is going to be 7. I thank you very much for your attention. As always, have a good one.